Okay, in this video I'm going to talk about the Darboux theorem. So basically, this is the statement. So let's say that we have a function f from a closed interval ab to the real numbers, and suppose that f is differentiable. F is differentiable like on AB. Then this implies that the derivative of this function has the intermediate value property. Has the intermediate value property, which means that like for any y that is between the derivative of at a and derivative at b. Well, like we don't know if the derivative of a is less than the derivative of b or greater, like either this or this. Like it's better to write this way. So either this or this. So like basically y belongs to the like the y is a value between the derivatives of f of a and f of b, regardless of which of them is greater or which of them is smaller. So for every y between these two values at the boundaries, there exists point C in the interval from A to B, such that the derivative at point C is equal to y. So basically, the intermediate value property means that like all values between the boundary values between f of a and f of b, they are attained at some intermediate point. So, and this is so there is a theorem that I proved in another video that says that this intermediate value property, it holds for any continuous function, and this Darboux theorem, it claims that the derivative of any function has this intermediate value property. So notice that the derivative, it doesn't have to be itself continuous. So the derivative of a function can be not continuous, can be not continuous, but still this property holds. So like if it is continuous, then this property holds by the intermediate value theorem. And like again, how to illustrate this property like visually. So like if we have a graph of a function, so like if we have, let's say here we have a, here we have a, and here we have b, then for any value y between f of a, well, in this case f prime. So this graph is not of function f, but of f prime, of the derivative. I guess we should put it here. So this is x, and this is the derivative of f of x. So between f prime of a and f prime of b, then this value is achieved at some point, is attained at some point c. So there is such c that for which the derivative is equal to this y. So like it cannot, the function cannot miss this value when it goes from this to this. It cannot miss this intermediate value. Okay, so let's consider the proof. So basically, the proof is that we consider another function, g of x. We consider it as f of x minus yx, and y is this value. So we fix this value y. So let's assume that, like, without loss of generality, so without loss of generality, we assume that f of, so the derivative f at a is greater than the derivative at b. Greater or equal. So without loss of generality, we assume this, and we fix, now we fix y such that y is between f of a and f of b. So f prime of, such that f prime of b is less or equal than y is less or equal than f prime of b. Like this. So yeah, so like if f prime of a is less or equal than f prime of b, then the proof is similar. So now we consider this function, and we notice that it is also continuous and differentiable, right? So this function is also continuous. Continuity follows from differentiability, so like it's enough to say that it's just differentiable on AB, because f of differentiable, and this is just a linear function, so y is here a constant, so yx is of course differentiable, and the sum of two differentiable functions is differentiable. But it is also continuous, because from differentiability it follows that it is continuous. So g of x is continuous on the closed interval. It is important that the interval is closed from a to b, and now we can apply the extreme value theorem. So by by the extreme value theorem. By the extreme value theorem, there exists a point C in the interval where the function such that g of c is the maximum of g of x on this interval. So that's exactly what the extreme value theorem says. So if a continuous function on a closed interval attains its maximum and minimum values at this interval, so attains like at some point. So this is exactly the statement of the extreme value theorem, and here we need the maximum. Like the extreme value theorem says that it attains both the minimum and the maximum at some two different points, generally speaking. But we need only the maximum, and the minimum would be needed like in the opposite case. So like when we assumed here without loss of generality, so in the opposite case, I guess we would need to take the minimum if f prime of a is less or equal than f prime of b. So this point C where the maximum is the maximum of the function g of x, right? So now yeah, so now now what we need additionally to remove the equality cases, so like we can just consider them separately. So if so basically what we need is like the case, so y again, so like let's recall this. So y is between f prime of b and f prime of a. So if it turns out that y is exactly f of b, f prime of b, so if like we need to consider these cases separately. So if y is exactly f prime of b, then for the point C in the original theorem, like not to be confused with this C, but this C, like we need to prove the existence of C such that f prime of C is equal to b. So then we can take C in the original theorem, we set it to b. That's exactly what we need. Then basically f prime. So then f prime, well, like f prime of C is equal to this y. But like without writing this explicitly, like we see that, so if y is f prime of b, then this value y is already achieved at the point b, so attained at the point b. The derivative takes this value f prime of b at the boundary point b, right? So that's what we need. So but if y is f prime of b, then this value is already attained at b, and the same for A. So if y is f prime of A, then similarly. So basically these two cases are trivial in the original theorem. So we can assume that y is strictly between f prime of B and f prime of A, because the cases where y is equal to f prime of A and f prime of B are trivial in the original theorem. So now we can assume this, that it is strictly between. So now we go back to this, what we obtained from the extreme value theorem. So there exists such C in the closed interval that where the function g attains its maximum. Right, so so now we notice that this point C, so this C here, so this C, it cannot be A and cannot be B. Let's prove that it cannot be A and C is not equal to B. So why is that? Well, because in these cases, so the f prime so g prime of A is equal to f prime of A minus y, right? So when we, okay, let's write first the general derivative. So the derivative f at x is equal to so when we differentiate the function g, so it is defined like this. So when we differentiate, so first it's derivative of f, and then we have y, just a constant y, because the x derivative of x is 1. So that's the derivative, and in particular the derivative at a is f prime of a minus y. And because y is strictly less, so we can assume that y is strictly less than f prime of a, so f prime of a is strictly greater, so this derivative is strictly greater than 0, and similarly the derivative at b is equal to f prime of b minus y, and this is strictly less than 0, because y is strictly less than f prime of b. Strictly greater, y is strictly greater. So now, so if the derivative, so like so if the derivative is strictly greater than 0, then at this point, then this cannot be a maximum, because well, the derivative, so g prime of a is the limit of h to 0, h tends to 0 of g prime g of a plus h minus g of a over h. So when we approach this limit from above, so when we take h greater than 0, strictly greater. So basically when we consider the right hand derivative, then this would be greater than 0, and this would be so if g was if g of a was the maximum, so if c equal to a, this would imply, so c is the point where g attains the maximum, right? So if c were equal to a, then g of a is the maximum, therefore this g of a plus h is always less or equal, so this would be less or equal than 0, and so the whole fraction would be less or equal than 0. So and therefore it would be always less or equal than 0 when a plus h is within the interval from a to b. So then this whole limit would be less or equal than 0, but we know that it is greater or equal than 0 from this. Strictly greater than 0. So this is a contradiction. This is a contradiction that proves that c is not equal to a. So this is a contradiction. So this less or equal than 0 and this greater than 0 is a contradiction. That proves that c is not equal to a. So we assumed that c is equal to a. From this we concluded that this derivative is less or equal than 0, but it is in fact strictly greater than 0. So c is not equal to a, so the maximum is not achieved at the point a. And similarly, we proved that c is not equal to b by considering the derivative at b. This one, that it's less or equal than 0. If we assume that c is equal to b, we would get that this derivative at b would be less than would be greater than 0, greater or equal than 0. So basically we proved these two properties, that the maximum is not achieved at the boundary points. So then it is achieved at some intermediate point. So the c is strictly between a and b, or like another way to put it is in the open interval from a to b. But then we can apply the Fermat's extreme value theorem. So if it is maximum and if it's in the interior point of a and b, then by the Fermat's theorem, it's also called the interior extremum theorem. So it is the maximum. So g of c is the maximum of g of x, and of course it is a local extremum. So g, let's write here. So g of c is the maximum of g of x, and x is an AB. Therefore, C is a local extremum. If it's a global extremum on the interval from a to b, then of course it's a local extremum as well. And it is an interior point, which is important for the Fermat's theorem. By the Fermat's theorem, then g prime, the derivative at the point C at the local extremum is 0. And from this it follows that, we recall what is the derivative of g. The derivative of g is this. So it is so this would be equal to f prime of c minus y, and this is equal to 0. So from this it follows that f prime of c is equal to y, and that's exactly what we needed to prove. So we found an intermediate point c where the derivative of c is equal to y. Yeah, so this condition is what we proved. Yeah, so basically the main idea is to consider this function g of x and to apply the extreme value theorem and then the Fermat theorem for this function, but we need to be careful to separately consider the boundary cases when y is equal to f prime of a and f prime of b. So maybe maybe I had to consider these cases at the very beginning of the proof before I introduced the function g. That would be clearer. The proof would be cleaner this way. Yeah, so this is what we needed to prove. So that's it for this video.